Microphone should be
working?
Yeah, it should, yes.
So give it
Do you need
one of
sound?
your USB-C. I will.
Do you need sound, Daisuke? Because then
Sound?
you have to connect with the...
Sound?
Do
You
need
don't
sound?
have any video with sound, right?
No, I
Okay,
don't.
that's fine. Yeah, so now.
It doesn't seem to react.
So let, yeah, no. Connected. Yeah, it was not connected. Now it's all connected. Oh, okay. So just allow. Yeah.
Okay.
So this is forward, this is backward,
Okay.
and the top one.
Thank you. I think I'm all set.
Okay. Okay, welcome everyone for the final weekly colloquium of this semester, and we are extremely happy to have Professor Daisuke Nagai from Yale University as the speaker today. Thank you all for coming at a slightly unusual time, which is our usual time is 2:30. Since one of our own, Professor Suchetana Chatterjee, was a collaborator and a postdoc mentee of Professor Nagai. So I invite Dr. Chatterjee to introduce Professor Nagai.
Thank you, Rituban. First of all, a lot of thanks to Daisuke for coming to presidency, visiting presidency, and giving this colloquium. We are very thankful, very grateful to have him here. So if I start talking about Professor Nagai, then I don't think we can have his talk. So I'll briefly just tell that Professor Nagai was an undergraduate student at University of Michigan. And then he did his PhD from University of Chicago. And after that, he moved as a, I think, Fairman Schwarzschild, right? Something that's the pronunciation. Price postdoctoral fellow at Caltech before he joined Yale in 2005. 2008, sorry, 2008. 2005 is when you got your PhD, yeah, 2008. Now, I know even before I was his postdoc at Yale, I knew him because I knew his papers, and I knew him because he actually visited Pittsburgh to give a job talk, and that's when we interacted. Pittsburgh also offered him the job, but unfortunately we couldn't have him. He joined Yale. So, so during that talk, I was like super awed. That this I always tell to my students that that was the first, well, not the first time, but one of the first times I saw a speaker, a job talk speaker coming and giving a talk where every question, so whatever he speaks in his slide, and every question up to third order, the answer is known to him. So that was like super, super impressive. And I was totally awed. And then when I went to postdoc, I'll just say a couple of lines. So the reason, one of the reasons that I'm standing here today, I'm a faculty member at prestigious university, and I am able to do whatever I could do, little I could do. A lot of it is, I think I owe it to Professor Nagai. So when I joined Yale, I was like, I was a curious student, and quite upset about, I worked on a thesis which was the SD effect of AGN feedback, and that will never be detected. This was like, I should throw my thesis it's a very like theorist fact, imagination. It will never be detected. I should throw it in a dustbin or something like that. This was the level of confidence that I had. And then the first time after joining Yale for like, I think it was like a couple weeks after I joined Yale, there was a discussion with Professor Nagai, and I was like, my God, it seems interesting. I have done some interesting work. So that was the first, thing that came. And then later, I wrote it, I think, in one of my posts, and I always say that the transformation from a curious graduate student to a scientist who has a purpose. I mean, so I will just quote one conversation I had with Daisuke that, look, you can never make an excuse to not work hard. You can never make an excuse to not do research. Even if you go to a community college, you have to do it. First, you have to learn what is excellence. So that's the learning lesson I had working with Daisuke. I could have never, I mean, if I could do good science or not, that's a different story. But what should I achieve? What should I aim to achieve? I think that was primarily set by my interactions with Professor Nagai. He too was a very young faculty at that time, and we did spend a lot of time together. So I owe a lot of my, professional scientist career to this gentleman, and it's a great honor for me that we could have him here today at presidency. The another one thing that I should mention, apart from science, is my introduction to sushi. So I didn't use, I was like, I had the inhibition, although I liked fish, but I had the inhibition that, oh, this sushi thing I can't have. And I think Daisuke invited us, his group, to his house, and Daisuke's wife, Miki, who happens to be also a good friend of ours, she made like fresh sushi. And that's the first time I had a sushi, because you go to a guest house and she prepares something so kindly for you. You have to try it. I have to try it. I was like, oh, wow, this is nice. And then for the next few years, sushi became one of my favorite dishes. So it's science and sushi, and there is something else that we were talking last night that I don't want to discuss in a public colloquium. But I think I have spoken a lot, and so it's a great pleasure that we have Professor Nagai here today, and we'd be very interested to hear. I'm meeting him after 12 years to his work on what's the latest development in cosmology using multi-wavelength surveys, and of course, AI and machine learning. Thank you very much. Thank you so much.
Well, thank you very much for such a generous introductions, and it's a pleasure to actually be here and have a chance to actually share the time and reunion with Ritban and Suchatana. It's been a while, and I've been extremely impressed what they're building here in the School of Astrophysics, and all of the effort and all of the students, all of the program. It's just truly impressive, and I'm very delighted to see that just new school that are just thriving. And I wish you all the best with this really exciting development that you all are having with their leadership. So thank you for having me. And I would like to share some of the things that I've been excited about over in the area of cosmology. And I would like to start with this picture that many of you may have seen. So I'll try to, maybe for the first half of the talk would be fairly, hopefully introductory, some of the things that you might know about, but I just wanted to set the stage before delving a little bit more into technical aspect of things and latest development in the second half of my talk. Sort of this is just a one slide summary of where I think we stand in the in great triumph in cosmology, starting from the initial condition of the universe at redshift 1000, when the universe was very small. We have a well-defined initial condition, and we've learned a great deal about cosmology, the composition, geometry of the universe from using cosmic microwave background. On the right-hand side, on the other hand, is showing a distribution of matter in the universe mapped out by galaxy survey. It's a small digital sky survey in optical telescopes. And we know today that universe started with the tiny ripples of fluctuations in the early universe, which has underwent the gravitational instability in the expanding universe and led to formation of very inhomogeneous, highly nonlinear universe that we see today. So the universe looks very clumpy, looks filamentary, looks kind of like a neural network or neural in the brain, which consists of filaments, voids, and also nodes at the intersection of those filaments. Now we have a standard model of cosmology known as lambda CDM. Lambda stands for cosmological constant. CDM stands for cold dark matter. And we know the number of these constituent very well. The cold dark matter makes up about 23% of the universe, dark energy 73%. Things that we thought we knew from particle physics over the past century, which was also the standard model of particle physics that is just beautiful and amazing. But yet the things that we know about from particle physics at the end of the century and even today only makes up about 4% of the energy density of the universe, which gives us, we have a beautiful standard model of cosmology, but 64% of the material in the universe is something that we do not yet know. So it's really, when we look into the universe, we've learned that we are only looking at the tip of the iceberg using the particle physics experiment, and that we know by looking at the universe that there is so much more to learn underneath the tip of the iceberg. We are in the venture of trying to understand those entire iceberg, what the universe is really made of, and that many of us who are in cosmology field are inspired by the fact that there's so much more to learn about the universe, and the goal is to try to develop a technique, strategy, survey, simulations to see if we can unlock the mysteries of the composition of the universe. So that's a big question that we are grappling with today, and it's driving much of the field in cosmology. The one thing that I can say about cosmology, that cosmology is no longer a theoretical subject where you theorize, philosophize how the universe is made of and just talk about things. No, it's not really. The subject has evolved significantly that now it's a data-rich area. We have so much data about the universe. In fact, the initial condition of the universe that I showed earlier in cosmic micro background is extremely well characterized. It's one of the rare situations where we have extremely precise initial condition of the universe. We also have a working model of the dynamics of the universe given by the Einstein's field equations. So if you have initial condition, if you have equations, the motions, all physicists know that we can solve this equation, propagate in time using high-performance computers, and we can actually develop a very detailed model of structural formation of the universe. So starting from the initial condition, we can predict the large-scale clustering statistics in the present-day universe, for example. Now, so that's a theoretical aspect of things, especially using high-performance computers. You can actually make a very detailed quantitative predictive models in the area of computational cosmology, which is the topic that I work on. On the other hand, these computational models could now be tested in this era of multi-wavelength cosmological surveys. I just list only a few of the surveys that are going on from optical, from DESI. Rubin is the telescope that's coming up in the US. Euclid, which was recently launched from the European Space Agency, doing galaxy surveys in optical and infrared. Also, microwave, the next generation of Simon Observatory, CMBS4, our next generation CMB experiments, which are under consideration, under development. Simon Observatory will be taking data very soon. Also, there's a telescope in X-ray. One of the recent example would be Rosita telescope from Russian German mission, which has been taking data, doing all-sky survey in X-ray, really going into the much higher, improving sensitivity and angular resolution compared to the previous generation of ROSAT survey. And then, of course, in radio, in GMRT has been a workhorse for understanding non-thermal phenomena in cosmic large-scale structure, galaxy clusters included, and then the next generations of radio telescopes are underway. SKA is the major investment worldwide, including India, which will be pushing the frontier of radio, the microwave, the optical, and X-ray. So this is sort of what I mean by multi-wavelength, era of multi-wavelength survey over the next decade, perhaps longer, but very likely longer. So these are the fields for many of the young people here that it would be significantly data rich. The challenge would then be to actually develop machinery, theoretical models, computational models, possibly using artificial intelligence or machine learning to unpack these large data sets that will be coming from over the next few decades. So there's a lot to do in terms of data. And the way that the cosmology works these days is to basically have two types of large data sets. One is from telescope, which is taking petabytes of data to study, for example, the distribution of galaxies or distributions of gas. Also, you can study the distribution of dark matter through gravitational lensing. And then you take those observational data, you apply some statistical inference, for example, calculating 2-point correlation function, taking 2 points and calculate power as a function of separation. You can actually then construct, sometimes people construct summary statistics like 2-point correlation functions to reduce the data into sort of easy to understand quantity. And then you want to then compare with theory. On the theoretical side, since we only have one universe to observe, that it's a bit difficult to do experiment on the universe. We can observe, but a lot of experiment actually is done in this area of cosmology using high-performance computing. These are numerical experiments. And what you do is you start with the initial condition, which is given to us, and then we know how to also solve the Einstein's equations, and then propagate the distribution of matter in time under gravitational influence using n-body simulations, for example, basically representing matter using the particle, and then to study the interaction between n particles through gravitational dynamics, solve those equations forward in time in the expanding universe. You get a simulation that looks something like this, that looks kind of resembles the distribution of galaxies in the universe today. And then you can apply similar kind of statistics that you apply to the distribution of the observation. And then you use this thing called Markov chain Monte Carlo, some statistical technique to then do this thing called inference. Now, in simulations, you can change the Einstein's equation, you can change gravity laws. Yeah, some people do modify gravity calculation by adding additional term to the Einstein's equations, and you can develop a universe that are quite different. You can do self-interaction, dark matter. You can change the properties of dark matter. You can change properties of dark energy. All of those experiments are often done in simulations by changing those parameters in equations. And then that you eventually want to do the inference by simulating many volume. You want to do inference to see which universe actually matches better with the data. So this is the sort of the workflow of how we do cosmology using large data sets, both large data sets from observations, large data sets from simulations. Those are key ingredients. And then there are a lot of, there's sort of each of these are observational cosmology, computational cosmology, or a field on its own, which I will tell a little bit about in terms of what we have learned. So this is a simulation of the Millennium simulation, one of the larger in-body cosmological simulations, which shows what that distribution of dark matter actually looks like. And one of the striking feature is this thing called galaxy clusters, which is the largest gravitational bound object that forms at the node of cosmic web, which consists of filamentary structures. There are little groups and galaxies that are embedded within each of these galaxy filaments. And then there are also regions with a fairly empty region called voids. So the most massive object called galaxy clusters are particularly sensitive. For example, the number density of, so you can actually use galaxy clusters to do cosmology. And the idea for doing this is, oops, sorry, I think it has frozen. Just give me one moment. Okay. So the idea for using galaxy clusters to do cosmology is quite old. It's been around almost 90 years or more. In 1933, the Fritz Zwicky, he was actually studying the motions of galaxies in coma clusters. And by studying the dynamical mass of the coma cluster and comparing it to the mass of the stars that he can see by counting stars in these galaxy clusters, he knew that some mass is missing, that something like dark matter would have to exist even back in 1930s. Since then, we've seen rotation curve of galaxies in Milky Way, which also indicated that there needs to be some additional mass included, more than just what we can see in the stars. So that was sort of the led to the acceptance of the dark matter. What's more recently using galaxy cluster, especially this thing called merging cluster, we've actually learned that the dark matter really does seem to exist, and then that we cannot explain away just this phenomena just by changing gravity laws. Just by using modified gravity cannot explain this morphology of this thing called bullet clusters. The reason is that what's shown in red is a distribution of baryons in the form of hot X-ray-emitting gas, and those are most of the baryons in the universe. On the other hand, the gravitational lensing indicates the mass distributions are located in this blue region, and then the baryons and dark matter, most of the mass, seems to be offset. You cannot describe this morphology simply by modifying gravity if the mass of the baryons are the source of the gravitational potential. So just with a single snapshot, this is a beautiful example that indicated that something like dark matter would have to exist. We don't know what it is, but the baryons cannot be the source of gravity. That's in the case of this merging cluster. So that was a very nice, just to take in picture, you can actually show that dark matter exists is a very beautiful example. Now, you can also use the galaxy clusters as a force balance test to actually to study dark energy. And the way that this works is that the formation of galaxy clusters, which form through accretion of material through the cosmic web, the rate of formation or mass accretion is sensitive to the gravitation, is basically governed by the gravitational force given by mostly dark matter and a little bit of baryons. And that gravitational force is counteracted by the repulsive force of dark energy, which is causing the accelerated expansion of the universe, which we have come to know in the late 1990s. So we can do this force balance test. It's just that it takes a many billion years in order for you to see this, to do the force balance test. It might be a little bit longer. You have to find a very long living graduate students to do this force balance test. So any of you who are living for billions of years, you can do that experiment. Most of us who can would have to do this using statistical way. And the way that we do this is to use the finite speed of light as to our advantage. The fact that the speed of light is finite means that as you look deeper into space, you're looking back in time. So when you look back in time, then you can study the evolution of the large-scale structural growth. This is a simulation where an in-body simulation of dark matter, where at the present day universe, the redshift of 0 is designed to have the right number of galaxy clusters, and then you do simulation without dark energy, with dark energy, and then this is an illustration that shows that without dark energy, it's the gravity is so strong. There's no, in absence of repulsive force, counteracting force, you expect the structure to grow very rapidly. So in order to form this many clusters, there aren't that many galaxy clusters in the high redshift universe, let's say redshift of 1.4 in this case, compared to the universe that has that repulsive force. The growth of structure is slower because of the presence of the repulsive force. So just by counting the number of objects per unit volume or number density of these peaks given by galaxy clusters, just by comparing those maps and just go and observe them, you should be able to actually tell whether there's dark energy or not. And if you do more quantitative analysis, you can measure the properties of dark energy as well. So this is called cluster counting test. And this is one of the popular way of actually doing cosmology, especially for constraining dark energy and dark matter content. So there are many ways that you can do this. First of all, you can use CMB, cosmic microwave background, as a backlight. Just to show that how exciting this field of cosmic microwave background has been. The CMB, as many of you know, was discovered in 1963. Since then, the first satellite, COBE, was launched in 1990s with the 10 degrees resolution. So the resolution, angular resolution wasn't great, but a couple of Nobel went here, two went there for measuring the very beautiful black body power spectrum, as well as the finding of anisotropy. And then since then, in the following decade, sensitivity has gotten significantly better with the WMAP. And then the angular resolution also improved from 10 degree to 1 degree-ish scale. And then another decade, the Planck was launched, and then the latest CMB maps from Planck, all sky map, looks stunning with the even better angular resolution. Sensitivity is also going down by order of magnitude each time. This is just to show that what the experimental cosmologists, what experimentalists can do. Just imagine how many orders of magnitude we have gone down in terms of sensitivities and also the angular resolution. Each decade, you see something completely different. I think this just really convinces me that you cannot underestimate, no matter how small the signal is. I'm sure many of you probably have been impressed with the LIGO experiments, and that even the small strain can be detected. The same is true for CMB. There's even, no matter how small the signal may be, the experimentalists, once there's a good reason for it, they can develop this experiment that will eventually find it very well within your life. So if you see any interesting signal that are potentially clean, if you find it, then you're gonna be able to see it. So that was very encouraging. That this field really has shown us that the huge creativity and capability of humans to be able to advance experiment in just extraordinary way. Not just in some incremental factor of few, orders of magnitude and resolution sensitivity is all possible. Now, what do you do with all this cosmic microwave background? One possibility is to actually use this as a backlight. So as I said, one interesting effect is the inverse Compton scattering of CMB photon with hot electrons embedded, for example, within galaxy clusters. Galaxy cluster is the largest gravitational potential well. And when you throw the hydrogen and helium plasma into the gas, you heat it up to 10 to the 8 Kelvin. Temperature is so high that all of the hydrogen and heliums are ionized. Electrons and protons are in the plasma form and they're in soup. So there are a lot of electrons, free electrons, which can cause inverse Compton scattering of CMB photon. What that means is that the number of photons is always conserved, but the number that some of the photons, when they interact, they get upscattered. So it causes this thing called spectral distortion. This is an original black body spectrum. And then, so all of these photons get upscattered and then creating this sort of unique spectral signatures. At the 217 gigahertz is where this thing called a thermal null, there's nothing happens at 217 gigahertz because you're conserving number of photons but shifting up in energy. So there will have to be a crossover, and which happens at about 217 gigahertz, nothing happens. Below that, you see hole in the CMB sky in the direction of galaxy clusters if there is a hot electron. And then above 270 gigahertz, you see additional CMB flux, which is kind of really cute way. So if you have a 3 frequency, one here, one here, one here, maybe more, you can it's an unmistakable signature. Not too many other there's almost no other physical mechanism will create that kind of signature. So you look for hole in the sky in low frequency, you see additional increment in sky in CMB. And nice thing about this is that this is redshift independent, because that this shift spectral distortion happens as long as galaxy cluster exists somewhere in the universe. So it doesn't tell you where the clusters are, but that this effect happens regardless of where the redshift is. This is unlike X-ray emission, which is an emissive source. So if you place the light bulb, like X-ray light bulb, farther and farther away, it gets dimmer. So if you go to high redshift, the X-ray clusters typically gets much dimmer, while SZ effect is redshift independent. So this is an excellent way of finding high redshift galaxy clusters. And it's been many of these SZ effect or cluster has been detected using Atacama Cosmology Telescope, South Pole Telescope, and Planck survey. There are about thousands of objects has been found, or galaxy cluster has been found using this technique. So, and because of that, the people are excited about developing next generation CMB experiment called CMB S4 and CMB HD, different kind of survey. This is what people have detected so far with ACT, Planck, and SPT, mostly about 2 times 10 to the 14 solar mass, or about out to about redshift of 1.5, sometimes out to redshift 1.8-ish. These are the cluster sample that's been detected, and then the experiments are being built in order to lower this detection threshold down even further using CMB S4 deep survey. And the goal is to, once you count number of clusters, constraint cosmology, you can get constraints on equation of state of dark energy. Neutrino mass is one of the exciting constraints. And when you combine the CMB S4 with this thing called DESI, the optical survey, then you can really constrain the neutrino mass at the level that you can then test the inverted hierarchy of neutrino. It's a big problem in particle physics that the total mass could be constrained, that might shed insight into neutrino physics, even from the cosmic frontier. So this is one of the very exciting problems. Yes.
So those rate points are actually of the pink ones, the S4 ultra deep, right?
These are Planck. These points are all existing measurements from Planck. These are Planck, ACT, and then the black one is SPT. These are all these lines are the expected S4 ultra deep field. Will lower the mass threshold down to about 10 to the 14 solar masses out to redshift of 3. So you can find, for example, protoclusters. If there's a massive amount of protoclusters at high redshift, then you should be able to find that too. Yeah. And please feel free to ask questions. I don't intend to cover a lot of material, but I want to make sure that we convey some of the exciting frontier here. The other thing that we could do when we are using Sunyaev-Zeldovich map is to do analysis that's analogous to what people have done using primary CMB. What CMB community has done is to compute this thing called power spectrum, because these are Gaussian noise. The Gaussian can be characterized by only 2 points, or just use, you only have the mean and then the dispersion. You only need 2 numbers. So if you compute this thing called the power spectrum, or Fourier transform of 2-point functions, that should have all of the information that you need for Gaussian signals. So that's a nice thing about the CMB power spectrum. You compute the power, and then you've seen this kind of figure in cosmology course if you have taken one. The first peak tells you something about geometry of the universe. You can use this second peak and to actually measure the baryon, how much baryon in the acoustic oscillation that's causing the acoustic oscillation universe. And then there's a lot of information about large scale structure. And then, we have learned a lot of cosmological parameter with this exquisite precision. You can has provided a lot of constraints on the cosmological parameter that we know today. But you can do this kind of analysis also on the SZ map, the Sunyaev-Zeldovich map as well, and kinematic SZ map, which is caused by peculiar velocity of the dark matter halo. There are 2 types of Sunyaev-Zeldovich effect. One that's caused by the thermal distribution of electron, one caused by the fact that the clusters are actually moving relative to the CMB frame. That causes additional signal. And so you can so once you identify a galaxy cluster, remove them, do all the cluster counts, and there are some residual map that looks kind of like Gaussian. It's never perfect Gaussian like primary CMB. But they are noisy map. You can apply you can compute thermal SZ power spectrum, and then it's been done using Planck data. So that allows us to learn not just about finding galaxy clusters and count them, but you can actually do fluctuation analysis on the residual map, and that also contains cosmological information as well. So those are the 2 different analyses. There are a lot of creative things that you can do once you have CMB maps and extract the galaxy clusters and so forth. The other way, the X-ray band, on the other hand, is equally exciting. So the one that's driving this field is eROSITA, but there are previous generation of observation which has provided a lot of insight. The X-ray photon comes from the thermal bremsstrahlung. the electron moving in the electric field of protons causes this the deceleration of electron leads to emission of photon, and this turns out to be, for the 10 to the 8 Kelvin plasma, turns out to be in X-ray. So there's continuum, and there's also the X-ray emission through the quantum transition. So the combination of quantum transition of ions and sulfur, heavy elements, as well as the thermal bremsstrahlung gives a rise to X-ray surface brightness emission that are detected using these telescopes. You can also measure temperature and metallicity from those spectrum. Interesting thing about that, this is sort of state of the art in terms of finding galaxy cluster using X-ray telescope. These are the data points overlaid on top of the SPT Planck SZ detected cluster, which are usually limited about 2 times 10 to the 14 solar masses. X-ray are very sensitive, so they are very good at finding low mass objects, especially at low redshift, because they get X-ray sources get dimmer as you go to farther redshift. So SZ starts to become more sensitive at the high redshift, but nonetheless, because the X-ray instruments are so sensitive, these are the initial galaxy clusters and groups that are detected using early Eurosita measurements, or EFEDs. So it's exciting that you can see all of these, find many of these objects that well below 10 to the 14 solar masses, all the way down to a few times 10 to the 13 solar masses. These are galaxy groups, smaller mass galaxy clusters. And with that, you can, these are actual constraints that was published from ERAS-1 in this year. And these measurements are continued to come based on ERAS-1. So that's a 1-year data. That's even more than EFED's data. That's 140 square degree. Now there's all sky data that was taken for 1 year. And now we're getting interesting constraints of W, omega matter, sigma 8, and it's getting to the point where it's trying to drive the cosmological tension discussion from that data. The last thing I would mention is the gravitational lensing. This is a beautiful image of the gravitational lensing due to galaxy clusters taken by JWST. The first image that Joe Biden showed when he was announcing the images from JWST. And so this gravitational lensing is a direct probe of mass distribution. So it's a really nice way of just directly measuring the amount of dark matter, which we believe that most of the mass is in dark matter. So there's a direct probe sort of dark matter. There are a lot of experiments coming online. LSST Dark Energy Survey is completing. LSST coming online with Rubin telescope. There's also in space, Hubble HST has done a lot of created a lot of great images, but JWST is making this image even sharper. And then the Euclid is another European mission, which is designed. One of the key science goals is to actually do cosmology using these gravitational lensing. Not just these strong gravitational lensing arc that we see here, but as you go out to larger radii, you see this thing called weak lensing. It's a small shear that is caused by the mass distribution universe on background galaxies. Now, this cosmic shear, which is due to weak gravitational lensing in the large-scale structure map, is kind of interesting when you actually one of this thing called SA tension. SA is a combination of two cosmological parameters, sigma 8 and omega matter. And because sigma and omega matter has this banana degeneracy, so when you combine them, you can just make everything flat. So SA is a good convenient parameter as a function of omega matter. It's flat in this figure, and that there's this one of the cosmological tension analogous to H0 tension, Hubble tension, which is driving this cosmological field, because if there are tension between cosmic micro background and growth of structure, that's the tension that we're talking about. So we're comparing always with a Planck cosmological measurement from primary CMB that I was referring to earlier. Now you're using the late structure formation measurements to see if you get the same answer. And sometimes you might expect different answers if the cosmological parameter is different from the standard lambda CDM. So looking for this tension is a way of finding the physics. And in fact, there may have been some tension, although the error bars are still pretty large. There has been some reported tension, but the problem with this technique and many other techniques is this, and one of the problem, PSF, of course, is a serious problem. That in order to measure shear, you really need exquisitely accurate PSF, which is extremely hard to get. That's an instrumental problem. But there is also the theoretical problem called baryonic effects. And this figure shows the problem of the challenges for this technique, which basically computes the power of matter power spectrum, the amount of power on different scales, from large scale, small k means large scale, large k means small scale. And when you compute the matter power spectrum in the universe that has galaxies and baryons in them, and compare that matter power spectrum as a function of scale to universe that doesn't have any baryons in them, n-body dark matter only simulation, which is what we typically like to do because it's simple. Baryon physics, when you turn on galaxy formations, it gets complicated. But then the point here is that when you look at this hydro simulation compared to dark matter, there's a difference. If everything aligns, then if it's one, it's a very simple story. But when in the universe that has baryons, it tends to actually causes the power to be suppressed on large scale, and then it's significantly enhanced on very small scale. What's happening is the galaxies are cooling the baryons and basically causing a lot of materials to flow in. Baryons to flow in, that's how you form galaxies. So on small scale, on the galaxy scale, there's a lot of power enhancement because of the motions of these baryons, causing those cosmic web baryons, missing baryons, all falling all the way in to form galaxies. So that's what this effect here over here is. But because the galaxy formation process caused these baryons in the intergalactic medium to fall in, that you get suppression of power on large scale. So this is all due to the galaxy formation physics. And
galaxies don't calculate, sorry, for density, what is del square and the power?
So delta is the matter power spectrum. Yeah, so this is the matter power spectrum. It usually comes in square. So that's what we're looking at. Now the point of this, however, is that you can take the state-of-the-art hydrodynamical simulation that has these galaxy formation physics in it. Illustrious TNG 100, 300, ALS, Horizon AGN, no AGNs, you can turn them on and off. If you don't turn on AGN, then you just get a lot of power in the center. So that's interesting. Original Illustrious, which is known to have significantly less reduced gas fraction, or significantly has a strong galaxy formation, which has the sort of biggest effect, and wins is evil. The point is that there's no good convergence among the state-of-the-art simulation. So this is one of the big challenges, is that you can see that the power at k of 1, for example, is affected by, in some cases, just only a few percent. But in some cases, it could be just as much as 5%, maybe 20, 30%. We cannot do precision cosmology if some of the baryonic effects at the level of tens of percent. Yes. Yes. In most of these simulations, the models are collisionless dark matter. They have not changed the nature of dark matter. Usually, for example, if you do self-interacting dark matter models, they tend to actually cause the density profile in the center of the halo, make the cuspy halo a little bit more core because of the self-interaction. So that kind of self-interactions are usually seen in central regions of galaxy clusters, or sometimes it could be seen or pronounced in dwarf galaxies, very small object, which is not contributing too much in this area. Most of the powers are coming from galaxy groups and clusters here. So that we expect the dark matter, for example, something like a sample dark matter to have fairly little effect we expect that to have like effect around here. It's only in very small scale because we're talking about core dark matter halo due to sample interaction of dark matter, and that would happen in about 1/10 the virial radius, which would affect power on a fairly small scale. So all these simulations, that's correct. That's correct. So for these simulations. So we don't really know. There are a lot of parameter in the dark matter model, so you can you might refer to that itself also enhance some. Okay. So the primordial black hole, I do not expect the primordial black hole to affect the growth of structures too much. It kind of, although they are larger than dark matter particles, otherwise the black holes and even compact any sort of stellar object, they behave collisionlessly. And that's what the N-body simulation does. The primordial dark matter, if there are dark matter turned out to be made of primordial dark matter, this result probably is unlikely to change. You have to do something that causes the distribution of dark matter somehow, and the constituent doesn't matter. But any interaction within dark sector that could actually cause changes in this power spectrum. Okay, so that's sort of the intro. I'm not sure how much time I actually have.
It's fine. We have
20 minutes. Okay, so then I'll go a little quickly. So that's the landscape of cosmology in the era of multi-wavelength survey. I think we're really entering into the golden age of data-driven cosmology with large simulation, or so far only talk about a large set of observations. The new frontiers are, we've learned a lot from large-scale structure, baryon acoustic oscillation, cosmic microwave background. But a lot of new data that we're going to be talking about are going to be on smaller scales, but they're inevitably non-linear. The largest of which would be probably clusters of galaxies. These are virialized, cosmic wave are even larger. And then that there are also galaxies. These are the objects that we're going to learn a lot from these upcoming data sets. Now, that is a very difficult, challenging, multi-scale, multi-physics problem. We need to actually learn how dark matter halos are populated by galaxies, but we also need to worry about how much of these gas, which has been elusive. We have been having missing baryon problem, where a lot of the baryons are in the form of diffuse gas, which has been very difficult to detect. Galaxies, we can find them in galaxy survey, but the gas has been elusive, although the situation is changing very rapidly. I would argue that in this new era for the next decade, there are a couple of frontiers that we need to explore simultaneously. Computational frontier using hydrodynamic cosmological simulation is always the working force in terms of understanding and elucidating physics and making that very detailed prediction. So we definitely continue to push on that. We also then, however, the computational efficiency might not be there to actually meet the kind of survey that we need to model. And so I will talk about maybe two of this. One is the computational frontier and what are some of the key challenges. There's also modeling and also machine learning. And maybe I will jump because of the time, I will jump to the low noise, high resolution frontier, as I argue that the sensitivities are expected to grow very rapidly. And the resolution is also expected to grow rapidly. And it leads us to galaxy cluster cosmology eventually will become studies of dark matter, gas, and stars in this thing called circumgalactic media. These are the diffuse gas that are embedded within the Milky Way size object or even smaller. And those are the main source of baryonic effects that I talked about. The things that we don't know are due to those, what's going on in that area. So maybe one way to do computational, so hydrodynamical simulation is one of the way to understand how various multi-scale physics actually work. This is sort of what we've been doing this galaxy cluster simulation within our own group, working also with many other groups around the globe. And we have learned that the central regions of galaxy clusters are very complicated. They are regulated by the cooling and also heating, especially from active galactic nuclei, which blow out bubbles and cosmic ray. And that's one of the biggest challenges and in terms of understanding the cluster formation. But once you go outside of the one-tenth of the virial radius, the outer regions of galaxy clusters are actually not so affected, seems, by AGN feedback, but in fact, they are affected by this accretion process. Galaxy cluster forms through accreting material. And because they continuously accrete, there's significant level of turbulence and bulk motions, which gives rise to this thing called non-thermal pressure. These gases are not virialized. So this out of equilibrium feature actually is one of the biggest uncertainty in galaxy cluster cosmology, which invalidate, for example, hydrostatic equilibrium assumption, which can be used to estimate galaxy cluster masses, but the mass is expected to be biased by the amount of non-thermal pressure that you see in the outskirts. There are a couple of other features which I will highlight very briefly. Maybe I will mention just briefly that in the central region, the PRISM, which is a Japanese mission, which has been launched. It has extremely good resolution, a few EV resolution. It's capable of measuring that turbulence in galaxy clusters. So that's one of the exciting probes that are coming, which that was a press release from early March this year, and there'll be many more observations like this is from Perseus, but many of these observations will give us some direct measurements of turbulence and bulk motions in these galaxy clusters. In hydrodynamical simulation, we can compute the non-thermal pressure fraction, the amount of non-thermal pressure compared to total pressure, combination of thermal and non-thermal pressure. And the hydro simulation predicts that this non-thermal pressure increases systematically from center to the outer region, about 10% in the center, sometimes much less. And then there's the non-thermal pressure tends to increase monotonically up to about 30 to 40%. That's a lot of energies are in these unvirialized bulk and turbulent motions. Yes? Yes. So this includes turbulence and bulk motions. A lot of these are actually bulk motions, not so much turbulence. I'm happy to discuss a little bit more about the distinction between turbulent and bulk motion. Turbulence, of course, originates from hydrodynamic instability, bulk motion, not necessarily. A lot of these that we see, we believe is mostly bulk motions. And then the gamma is actually it's called the mass accretion rate. So D log and D log A, where A is a scale factor. So this is a way of measuring the accretion rate of the dark matter halo. And you can make a cut based on some threshold, larger than 2.7, less than 2.7. The exact number is not that important, but the point is that these are slowly accreting halo. They are much more relaxed. They hadn't had much major immersion. Any cluster that had a recent major merger would have a huge jump in mass. So D log M, D log A would be higher. So the gamma greater than 2.7 would be rapidly accreting object today, or the merging object. They tend to have much higher level of turbulent motion when they have a higher rate of accretion. And there's a systematic trend. The mass accretion rate of dark matter halo gives a rise to systematic difference in the amount of non-thermal pressure. This is a very important point. The other thing that we can see is that the dark matter halo ellipticity correlates with dark matter halo concentration. One of the things that we've learned from n-body simulation is that there's this concentration of dark matter. When you fit in the Nagai-Franken-White profile, you can measure how the dark matter is concentrated. Highly concentrated, low concentration, and then there's a large scatter. The scatter seems to originate from mass accretion history of the dark matter halo. Early forming object tends to actually be cuspier because they're forming in the high density universe in the early universe. So they tend to be cuspier. If about the late forming object that has a recent accretion today tends to have more puffed up feature because they're collapsing in the low density universe. So that's sort of the hand-wavy explanations of what gives rise to scatter in dark matter halo structure at any given mass. So that's why we see diversity of dark matter halo structure. And then we see that that is also imprinted in ellipticity. The recently accreting object is much more elliptic. And you can also see that feature in this scaling relation, temperature mass relation of galaxy clusters. There's quite a bit of scatter. We think that these scatters are actually driven primarily by the accretion rate of galaxy clusters. Late forming object would be less spherical, and then that they also have more non-thermal pressure. So that these pressure has not thermalized yet, temperature is still low because most of the energies are still in bulk motion. If you wait long enough, the bulk motion would dissipate, and then that its temperature goes up. So we expect those less spherical, late forming, highly accreting object today, therefore high non-thermal pressure. If you wait long enough, they move upward. So that's the evolutionary trend that we're expecting. This is the way that how this dark matter accretion rate gives rise to scatter in this thing called observable mass relation. Yes?
Dark matter simulation. I do not see this dark matter luminosity concentration. Like you were saying, this is related to baryonic.
Yes. So this is based on the hydrodynamical simulations. And then, yes, that we see the manifestation of this mass accretion effect on hydrodynamical simulation. A lot of scatter that we see in temperature mass relation, for example, this is easily observable from X-ray. We think that these scatters are actually probably, I'm advocating that a lot of this scatter could come from differences in mass accretion history of dark matter.
So in only dark matter simulations, you will not see this.
You will not be able to measure temperature.
That's what I can see
This one is from dark matter only simulation. This one is from hydro simulation. Sorry, it was a little bit confusing. Yes. So this one you can do with the dark matter only simulation, and this is what we did. This is the multi-dark quantum in-body dark matter only simulation on the left-hand side, and then there's also analogous thing happening in hydrodynamic simulation, but the quantity will be very different. We are interested in looking at the gas properties on this axis here. So we're trying to see if we can tell a consistent story between how dark matter formation is fundamental for giving rise to diversity of dark matter halo structure on the left-hand side. And then it's ellipticity as well. There's a correlation. And then how that is also driving scatter in the observable mass relation on gas. It's a lot of information on one side. The other feature that is interesting is this phenomenon called splashback radius. So splashback radius is the outer, it happens because the galaxy cluster is always growing, so potential is growing. The time it takes for the particle, dark matter particle, to come in and splash back out, that would take several billion years. So during that process, the dark matter potential got deeper. So if you have a deepening potential, then the particles see deeper potential to climb out, and therefore the particle cannot go out to infinity. There'll be a well-defined physical boundary for splashback. It's nice that it's interesting that there's an outer boundary to dark matter halo. And then you see this in body simulation if you go far large enough. There's also corresponding shock radius. This is the radius at which the gas is accreting for the first time. We measure this in hydrodynamical simulation. It seems that there's a bit of offset between splashback radius in dark matter and shock radius in gas. The shock radius is it's easy to see in this entropy jump. The entropy basically indicates that the presence of gas accretion shock. And you can see the gas is coming in for the first time and then shock heating. The shock heating is very amorphous. It's a little bit smaller here, it's larger there, very aspherical and directional filaments. So it's very amorphous. There's a lot more scatter in this relation.
Normalizing to the 200.
That's correct. That's correct.
Of the 8.
So and we're normalizing every splashback radius, shock radius of any given halo mass relative to that mass, then everything looks very universal when you use, especially when you use this particular virial radius definition.
That over redshift, the x-axis is.
So the x-axis is the mass accretion rate. It's the same gamma. So there's a dependence of the locational splashback rate mass accretion rate. If you have a highly accreting object, there's much more momentum. So it tends to push the accretion radius a little bit lower, or the splashback radius is smaller. For highly accreting object, there's much more like mass flux, momentum, that pushes things in. And there's that relation which has been well documented. It's been measured in many n-body simulation. You see similar trend in gas.
Gas is always a higher radius, a gas flow.
That's right.
That's also beyond radial radius.
That is, so R200 means very large radius compared to typical virial radius, which is more like this. Now, we're talking about accretion shock radius even larger than splashback radius. It's interesting. If you look at analytical equation as a solution to the secondary infall model, which might be appropriate for this kind of calculations, like Bertzinger solution or yes, they don't predict this difference. They're on top of each other. So it is interesting that you see something different, something additional physics is going on. It's an open research topic at the moment. The last thing I would mention is that the shock, accretion shock, is an interesting topic because it's basically this shock a collisionless shock. What that means is that basically what the shock does is that accelerates electrons and protons at the same speed when you see the shock. So then that the electron is 1800 times smaller, so almost all energy goes to protons. So when the gas is shock heated at this shock rate, accretion shock radius, all energy goes, most of the energy, pretty much expecting all energy goes to protons. And then that you have to wait for electron to interact with the proton through electromagnetic interaction. Now, if you can also compute the time scale for how long it takes for electron and proton to equilibrate. It's called electron-proton equilibration time. Now, that time is actually longer than the age of the universe. So you can see that the electron, it will take a very long time for it to actually equilibrate. So it means that you have a two-temperature plasma. You have electrons and protons are not equilibrated. It takes a very long time to equilibrate. So we did the two-temperature simulations and show that the average temperature of electron is biased relative to gas temperature. Typically, when you solve Navier-Stokes equation or use hydro equations, you're assuming you're making single fluid approximation, meaning that all electrons and protons in every element have the same temperature. That's not the case. So there's interesting plasma physics that you can do. And of course, we're doing this calculation based on Spitzer, meaning that unmagnetized plasma, then we get this effect, then we get these images. I think that if you talk to people who are working on solar wind, the electron can be heated inside of the collision shock as well, which of course has not been taken into account. So something like this is upper limit of what we can expect. It's possible that the electron can have additional heat inside of the collisionless shock, but this is very much the open area that we don't. Yes, so the turbulence is naturally included in the hydro simulations. Just the electrons and proton temperatures are followed separately. Okay, and then maybe I will mention. I think my time is running out, so I will just maybe 5 minutes. Okay. So one thing I would like to mention is I've been talking mostly about X-ray, Sunyaev-Zeldovich observation, the gaseous medium, intra-cluster medium in galaxy clusters. And then one of the exciting frontier is to do something similar to what I just talked about. Turbulence, collisionless shocks, and so forth. How in the circumgalactic medium, these are the warm gas which has been probed using, for example, the HST, Hubble Space Telescope, cosmic origin spectrograph using quasar absorption lines. This HST cost survey has been leading the field in terms of finding those diffuse gas, but which has otherwise been very difficult to study. But over the next decade, we think that this area of studying the circumgalactic medium will transform completely. Because of the emergence of new telescope, like we talked about, X-ray, we'll be detecting all of these warm gases and hot gases down to about, well, we've already seen the case down to 10 to 13 solar masses on individual objects. If you have a Eurosita, which will have 150,000 objects by the end of the survey, you can stack many of them around in the locations of groups, and then you can even lower the threshold to find, and there has been already first measurements of CGM from Eurosita, EURAS-1, and also EURAS-4 recently. So then you're already detecting CGM in X-ray emission, like in low resolution groups. You can also do the same for thermal SZ effect. If you do big survey, you can stack SZ effect, and you can detect the CGM down to about 10 to 12 solar masses. In addition to the absorption line, there's a new probe, fast radio burst. Maybe some of you might have heard. These are magnetar. You can use this to study the dispersion measure of polarized FRB source, and then as they traverse through the intergalactic medium, they rotate. So polarization rotate and gives rise to this thing called the dispersion measure. That is linearly proportional to electron density along line of sight. And that also can help us detect all of the electrons in IGM, intergalactic medium, and also circumgalactic medium. That's correct. So that's not the Faraday rotation. Sorry, that's not Faraday rotation, but it's a dispersion measure. So it's not so much the rotation, but there's a frequency dependence of that dispersion measure. So, but one of the exciting topics for studying the circumgalactic medium is this new set of simulation called CAMEL simulations, Cosmology, Astrophysics, and Machine Learning simulation. The exciting thing about this is that the collaboration has actually taken 25 H-inverse megaparsec box, fairly small boxes, but now they are capable of actually running, say, one of the illustrious TNG simulation 2,000 times by changing cosmology, omega matter, sigma 8, also changing the supernova and AGN feedback. There's a different kinetic and thermal energy mode in each one in AGN and supernova. So there are a total of 6 parameters, and you can run this many times and then create a training set that you can then feed into machine learning algorithm. You can, this collaboration has done this for illustrious TNG model, SIMBA model. It also has done it for Astrid model, and they're actually, right now they have already done this for about 7 or 8 sets of subgrid physics simulation, which I will show 4 of. So these are the distribution of gas density and also temperature in red in illustrious TNG, SIMBA, Astrid, and magneticum simulations. And so you can see that as the galaxy dark matter halo galaxy forms inside of those simulations, and then that it will do this supernova NGN winds. As you can see, the SIMBA has a very ejective, strong feedback compared to some other simulations. And in some cases that the feedback is heating up not just the circumgalactic medium, but also heating up the intergalactic medium outside of the virialized region of the dark matter halo.
Why is it 25 megaparsec? The size is 25 megaparsec.
This one is actually it's a cutout in the 25 megaparsecs. It's a little bit smaller than that.
What is that red color mean?
Red is the temperature, and the blue is density.
That means you have a lot of high temperature gas. That's because of the very high, AGN feedback modes of SIMBA.
That's correct.
It has a lot of hot gas,
Yeah,
more.
a lot of them is actually happening because the supernova is also very effective,
Yeah.
particularly powerful in these low,
Mass systems.
yeah, in low mass systems. So, so that's one of the things that allows us to do. You can basically write emulator. You can emulate what X-ray surface brightness of these galaxies should look like. You can also just look at where galaxies are in each of these simulations. You can look at this as a function of cosmological parameter, in this case, sigma 8, or you can study this as a function of supernova energy, or as a function of AGN energy. And that these simulation for the first time allows us to actually study observable as a function of cosmology and astrophysics. Instead of looking at one flagship simulation, which you typically have done in the past, for any given cosmology and just any given subgrid physics, you can just explore this and do this for many different kinds of subgrid physics model. So we think that this is one of the exciting frontiers. All of these simulations are supported by Simons Foundation, the Center for Computational Astrophysics in New York. We're doing this in collaboration with them. We're making mocks. And I think maybe one of the topic is that you can also compute the impact of baryons on matter power spectrum. And in this simulation, we see that this thing called gas spread. So how gas is spread relative to the original location of dark matter, which you can measure directly in simulations. And the farther away the gas spread, for example, if you have an extremely strong feedback, gas is spread out more relative to the original dark matter location, just because of the strong feedback. And in fact, the baryon spread is a function of the baryonic effect is a function of this thing called gas spread.
All these lines, the gas spread.
Yeah. So there's not much gas spread, there's very little feedback. You basically don't see any baryonic effect. The
gas spread to dark matter spread.
So you can measure how gas, in the initial condition, we identify where the gas is, and then finding corresponding dark matter particle. And then you can also measure at the late time where the dark matter particle is, gas particle relative to the original dark matter particle. You measure spread by finding the match between gas and dark matter particle at the initial condition and the late time. So this is at redshift of 0. So you can do only in simulations. Gas spread is difficult to measure in the real universe.
Changing the strength, but changing only the AGN contribution of it, or also the.
So here we're measuring gas spread. It doesn't matter what changed. It could be cosmology has changed. Maybe it might change some gas spread, and it probably doesn't. Supernova can do that. AGN do that. They're all. We don't really care what changes in parameter, but we are only measuring gas spread. Just how much spread has happened given the feedback.
When you are changing that parameter, you are changing the AGN feedback parameter or both? So
in this case, we looked at both. In one, we can change their supernova parameter. There are 2 parameters in supernova, 2 parameter in AGN. We change everything. It really doesn't matter which one we actually change. What we measure, what matters is how much gas spread is caused by any given changes that you make.
You cannot which feedback is actually causing the.
Just by looking at this, no. But that's the point, is that the most important parameter is not so much how each parameter is doing what. What matters is how much gas spread is actually made at the end of the day. That's the most important quantity, not so much what each individual parameter is actually doing. Is the lesson from this analysis. Okay. We can talk a little bit more offline about this. Now, there is actually, because that this gas spread is something you can measure in simulation, but it'd be nice if you can measure this in real universe. So this is, so we found one relation that would likely to work, and that comes from FRB. The fast radio burst has this special relation called McCord relation. This special relation basically plots the dispersion measure of cosmic contribution that's due to IgM and CGM. Now, there are other contributions, one from Milky Way, and then there's also one from the host of the galaxy. All of these contribute dispersion. Assuming that you can measure Milky Way and the host, you can then solve for DTM cosmic. Some attempts has been made. This is the early plot made by Makorda 2020. If you plot this dispersion measure cosmic as a function of FRB redshift, there's that relation. It's only a few points. There are many more points now. There's actually hard to see, but there's also the width. There's a dispersion around dispersion, and this is known as delta. Or we parameterize the dispersion of dispersion measure as an F parameter, the amplitude F. So the larger amplitude means there's a lot of dispersion from the site line to line. And then there's some redshift dependent factor to correct for. The point is that if you have very strong feedback, like you saw in the case of Simba, you homogenize the high density region with low density region. So you expect to see less dispersion, or F parameter is smaller for Simba simulation. If you have strong feedback, you isotropize density and temperature and kind of makes everything looks like a sheet of screen in the sky. When you look at the FRB sources in different sightline in a very strong feedback universe, because everything looks homogeneous, so you don't see dispersion around dispersion. It's just going to be a single line. Okay? So the stronger the feedback, we expect F parameter to be smaller, like it's almost like a line. If you have a clumpy universe and with very little feedback, there's no mixing anymore, then you expect to see large dispersion, whether you're going through CGM or you're going through void. They are very different. So there's a lot more, F parameter is larger when you have a weak feedback. So this is something we can measure by creating the dispersion measure map in different simulations. And then that we quantify the F parameter. How F parameter changes a function of each of the parameters. Cosmology, supernova 1, supernova 2, AGN1, AGN2 parameter. And we see that the larger the feedback or F parameter, weaker the feedback. This is strong feedback. The Simba simulation, strong feedback over here. And then it doesn't really change with the parameter too much. Other simulation depends more sensitively. For example, the TNG simulation depends on supernova 1. The stronger the supernova feedback, larger the F parameter.
But that is redshift dependent.
This is also redshift dependent. We're just kind of looking at this from the map that we generated, the LICO map so far. Now, here is the one lower limit. These are measurements on the lower limit from 78 FRB sources from the Baptista et al. And so you can draw a line here, and they didn't see anything. So F parameter is likely to be larger. Or there's a lower limit on F parameter. And it's kind of challenging the strong feedback model, though not completely. So, but this is the kind of measurements that we want to make in the future. Now, this is the work that we're just working on as we speak, but we decided to plot this F parameter for these 3 different simulations, and then plot this as a function of baryon spread that we were talking about. At the end of the day, for the cosmological application, all we care is baryon spread. And when we make that plot, it's a single line. So this is really nice. We think we found some universal law that allows us to use FRB measurements to measure F parameter. And then so if you measure F parameter and you can read off baryon spread, and in all of these lines, these are lines that has different cosmology, different feedback, different simulation, different subgrid physics. They all lie on this curve. So that's nice because, well, we know that the Simba simulation has a strong feedback, so it tends to populate, has a much larger spread, much smaller F parameter. But of course, F parameter and baryon spreads are somewhat related. In this scenario where feedback strength is the only thing that controls baryon spread and F parameter, which seems the case. And this is a case independent of subgrid. This relation holds. So that's nice because we think we found some kind of universal feature that allows us to use FRB measurements to measure F parameter, and then we can just read off the baryon spread for our universe and then correct it. So x-axis is the baryon spread that I was just talking about. So how much baryon spread between dark matter and gas particle? This is the same. Same. Well, I didn't actually introduce this, but that's like a typical baryon spread. I have to define about I'm happy to discuss maybe this offline, but so that's one area where we found some potentially interesting application of FRB, which is a new observation. The reason why I'm talking about FRB is because that it's a rapidly developing area, especially in observational cosmology. The CHIME is finding many sources every week. And within a year, you expect to see that sample of 9 or 10 to grow into hundreds. With the new experiment, it's also underway, and we expect to see thousands of FRBs over the next several years. So in the upcoming decades, in addition to X-ray and SZ, which we have been using to do cluster cosmology and also group cosmology, we can also imagine doing by combining also FRB along with SZ and X-ray. We think we can actually also perhaps even think about seriously, not just we're going to definitely learn about a lot of feedback physics in CGM and various samples, but I think there's also potential for using these new upcoming observations to do cosmology even using galaxies. So that's the exciting frontier that we see in these small scales. And I hope there'll be some discussion. Next in 2 days, there's a discussion on cosmology in the next decade discussion that we will be talking. I will be visiting IIT Indoor after today, and I'm also visiting the IUCA to discuss about the baryons beyond galactic boundaries. So these are mostly about talking about much of the measurements that we've been talking about, and see how we can actually turn this into a cosmological probe in the future. So, and there'll be many more conferences and like this, and I hope that you could. Many of you, I think, could relate because these are multi-wavelengths. So anyone working on from absorption lines, optical, radio, X-ray, we all have something to contribute. Anyone working on simulation is absolutely critical. So maybe I'll stop here and thank you very much for listening.
Okay, so there were several questions we get asked, but are there other questions?
Maybe in relation to what Dr. Molina said, you talked about in your simulation process, you talked about the interaction of dark matter. The prospect of interaction prospect can be allowed, not only for the interaction of dark matter, but also for the dark matter radial interaction. That also has to be taken into account.
That's right. That's a very much the research topic. Probably the best constraints on the dark matter interaction comes from bullet clusters. Dark matter baryon interaction maybe less so. I think that for a purpose of this matter power spectrum, it probably wouldn't play a big role because it only affects the small scale feature. But it's very much the ongoing topic. I think it would be interesting if we can use merging galaxy clusters. Like bullet, you need more bullet. You only have one object, but there are many. We know that there are many merging clusters.
Yeah. But available, I think you can get that in.
No. So merging clusters, I think we have only one bullet. So these two clusters merging.
Yeah.
So there are many binary merger clusters, 2146. In fact, this is the simulation from PNG cluster simulation, and these are massive merging cluster sample. And what is particularly interesting about merging cluster and promising in terms of constraining this cross section is to use something like a GMRT or SKA to measure this thing called radial relic. The radial relic gives you the current location of electron acceleration. You can see the location of shocks, and that the exact location and feature of shock depends on merger parameter. Mass ratio, impact parameter. What is one of the biggest problem of merging cluster is that there is a fairly large high dimensional parameter space. Mass ratio, impact parameter, speed. We need to know all of this in order to put the constraints on dark matter baryon cross section using merging cluster. But you might be able to actually get the exact timing, for example. There's also timing of mergers. And you can actually get a lot of those constraints when you combine X-ray and then also the radio observation. Radio observation tells you exactly where the shock is. So that gives you a lot of constraints on the merger parameters, which is needed.
So the results on the what is the limit of the
Yes.